This video is in the continuation with my previous video on PN junction basics. In that video we discussed about the formation of PN junction, and that when PN junction is formed, then a p-type material is having holes as the majority charge carriers and electrons as the minority charge carriers. So holes are in majority here and electrons are in minority. Similarly, on the N side, we discussed that electrons are in majority and holes are in minority. Right, so there is a gradient in density as we move from N side to P side in the density of electrons as well as in the density of holes. So here electrons are more and here electrons are less, so a diffusion current will flow of electrons from N side to P side. Similarly, holes are in majority on the P side and in minority on the N side, so a diffusion current of holes will flow from P side to N side. Okay, so this is shown here. The holes are moving from P side to N side and the electrons are moving from N side to P side. Now as these charge carriers leave their places, they leave behind ionized atoms. For example, if a hole moves from P to N, it will leave behind negative ions, and if electrons move from N to P, they will leave behind positive ions. So these ions are not free to move, and uh, therefore this region from where these charge carriers have left towards the opposite side, so this region is known as depletion region, because there are no free charge carriers here, only immobilized ions, positive or negative ions. This is also known as space charge layer. Now as this movement continues, the electrons move from N to P and holes move from P to N, and as they leave behind positive and negative charges which are not free to move, so an electric field will set up, shown by this arrow. So this electric field will oppose the motion of holes and electrons diffusing in the opposite side. So this electric field will tend to stop that current. Now when sufficient number of electrons left the N side and sufficient number of holes has left the P side, then this electric field becomes large enough because of these charges that they completely stop these movements of charges from P to N and N to P. Then the further movement stops, and finally we are left with this region where there is no charge carriers, and this region has a constant width, let us say W naught. So this we had discussed in the previous video. Now there are some formulae which we need to drive for the PN junction. because these will be used very often with the power electronics devices. So first we have to find out what is the charge density inside the depletion region. So as we discussed in our previous video, that let us say we added an a number of acceptor atoms on the p side, so it will generate approximately n number of holes per centimeter cube on the p side. So n is the density of acceptor atoms. It will result in Na density of holes. Now as near the junction, these holes move from p side to n side, so each hole will leave behind one negative charge. Okay, so if Na was the density of holes, so Na will be the density of the negative charges produced by the movement of holes from p to n side. So we can say that the density of negative immobilized charge in the depletion region is Na. Similarly, the density of positive charge in the depletion region is Nd, right? So this is written here, the density of charges from minus xp to 0. So this 0 line is here. This means the PN junction. So this 0 line, this 0 vertical line is PN junction. Okay, and then this distance is shown as xp. So xp is the width of the depletion region in the p side region. Okay, so from minus xp, that is from this point, to 0, that is to this point. So from minus xp to 0, they are only negative charges in the depletion region and their density is Na. Now if you want to find out the charge density, so since each ionized atom have one unit of charge, so the total charge density from minus xp to 0 distance is equal to minus q times Na. So I hope it is clear. Similarly, from 0 to xn, where xn is the width of the depletion region in the n-type material. So total width is xp plus xn. So xn is the depletion region width inside the n-type material. So from 0 to xn, the total charge density of because of these positive immobilized charges is q and d. So these charge densities are denoted by rho. Now we have to find out the expression for electric field inside this depletion region. So this is all depletion region shown here with p side here and n side here, and this is the junction. So now what will be the electric field in this junction? This can be derived by using the Poisson's equation. So you must have heard about the Poisson's equation during your electromagnetic field theory course in second year. So Poisson's equation says that the divergence of a gradient of potential is equal to minus of rho by epsilon. Okay, so this is Poisson's equation where V is the potential field which is a scalar field, of course. So this is the potential field. So the divergence of gradient of potential field is equal to minus rho by epsilon, where rho is the charge density. So this is the Poisson's equation. Now there is a relationship between potential and electric field, and it says that the gradient of potential is equal to minus of E. Okay, so this is a scalar field, which is potential field, and if we take gradient of it, so we will get a vector uh, electric field. So in our case, when we are talking in three dimensions. So in our case, uh, we are concerned with the distribution in x direction only, right? So if this is your PN junction material, so we are concerned with only this x direction. So if we take divergence of gradient of potential, so we can write it like this: d phi square by dx square. So this part will be equal to this: d phi square by dx square is equal to minus rho by epsilon, where phi is the potential field. So here potential field is shown by phi. Now also this expression will say that d phi by dx is equal to minus of electric field E, right? So if you put this value, if you put this equation in this equation, right, so you will get this equation. Because Q and A is rho, so rho here is Q and A, so this becomes minus Q and A by epsilon, shown here, and this is d phi square by dx square, and since d phi by dx is minus E, so this is dE by dx. So dE by dx from region minus xp to 0. So in this region dE by dx is this much, and in this region 0 to xn dE by dx is this much, because the charge densities differ in both the regions, right? Now we can integrate these equations, equation number 1 and equation number 2. So we can integrate it with respect to distance, and we can get this expression. It is very easy and you can do it in your notes. Now as you can see from here, from minus xp to 0, electric field has relationship with x with minus slope, with negative slope. So we get this slope in region minus xp to 0. Similarly, from 0 to xn, we get a line with positive slope. So in this region, from 0 to xn, we are getting a positive slope of electric field. So now if you want to find out the potential, so simply we will integrate E with respect to x, because d phi by dx, as discussed just now is equal to minus of E. So we just integrate E dot dx and then we will get phi. So similar thing is done. We have taken the integral of this electric field. So there are two regions. So first we will integrate E dot dx from minus xp to 0, and then we will integrate from 0 to xn, and then we will add them up, then you will get the total potential phi c. So if you do this, if you integrate this and integrate this and add them up, then you will get this expression for potential. Now this was the case when our PN junction is not biased. It is just formed and no external voltage is applied across the junction. Then this is the scenario. But what happens when we forward bias this junction? So again, first we have to repeat about the minority carriers. Now how do we denote various charge densities? So suppose that we have not applied any forward biased voltage yet. So let us say V is equal to 0. So in the P side, majority carriers will be holes and minority charge carriers will be electrons. So electrons will be denoted here as N P naught, where N means electrons, P means P side material, and naught means thermal equilibrium. Similarly, in the N side, majority charge carriers are electrons and minority charge carriers are holes. So holes will be denoted as P N naught, where P means holes, N means N side region, and naught means thermal equilibrium. Also, if you want to denote the majority charge carriers here, which are electrons, so they will be written as N means electrons, N means on the N side, and naught means thermal equilibrium. Similarly, here the majority charge carriers are holes, so they will be denoted here as P means holes, then again P means P side, and naught means in thermal equilibrium condition. So initially when voltage applied was 0, this was the density of minority charge carriers, that is electrons, which is denoted by Np naught, and on the N side this is the density of charge carriers, minority charge carriers, that are holes, Pn naught on the N side. When we forward bias this junction, we have some V, then an electric field will appear from P to N, because this side is more positive voltage with respect to this side. So an electric field, an external electric field will set up from P side to N side. Now this electric field will favor the diffusion process, because holes were moving from P side to N side when PN junction was formed. So that diffusion process will be supported by this external electric field because it has the same direction. The depletion layer width will reduce. Okay, so the width of the depletion region will reduce. So initially if the width was W naught, now the width becomes W, which is smaller than W naught. Now what happens, this external electric field drives the holes which are majority charge carriers. So it drives the majority charge carriers, that is holes, from P side to N side. Okay, similarly it will drive the majority charge carriers in the N side, that are electrons, from N side to P side because of this external electric field. Now as these holes reaches the N side, then we know that here minority carriers are holes. So these holes reaches the N side, and here the density of minority carriers increases because of this transfer of charges from here to here. Similarly, as electrons which are majority here reaches the P side, so here in P side electrons are in minority, so the minority charge carriers increases because electrons have reached here from the N side in this region. So I hope this is clear. So if you have any doubt, you can write in the comment section and I will try to address it. Now this is the density of minority charge carriers after the voltage V is applied. So holes move from P to N. So here holes are in very large number, which are in minority, but now they have increased. So near the junction they are in very large number, so density of holes here is very high, and as these holes migrate further inside the N side region, they will recombine with the majority charge carriers here. So what are the majority charge carriers here? Those are electrons. So these holes will recombine and their density reduces as they move further into the N side. So initially they have high density, and then as they move further inside the N region, their density reduces. So this is shown here with this curve. So initially holes have, which are in minority in N side, have high density, and then they recombine with the electrons and their density reduces. Similar is the case for P side region. So near the junction, density of minority charge carriers, that is electrons, is very high, and as they move into the P side, they will recombine with the holes and their density reduces. So this NP0 means electrons uh, in the P side at zero distance from the depletion region. So this is the depletion region. So NP0 is density of minority charge carriers from zero distance from the depletion region. So as the electrons move inside the p-type region, their density reduces because they recombines with the holes. And npx is the distribution of minority charge carriers which are in excess to this, that means which are above this. And similarly for holes, this pn0 is the holes in n-side region at zero distance from the depletion region. Now in this slide we will derive an expression for width of the depletion region, WV. So W is the width of the depletion region, and V shows the dependency of W on voltage. So VW means width of the depletion region for a given voltage. So we have to derive this. So for this, let us look at this expression. So phi c is given as qnaxp square plus qndxn square by 2 epsilon. So this is when no biasing is done. So this potential is when biasing is 0 volts or no biasing is done. But when biasing is done, let us say by V volts, so potential becomes V minus phi C. Now to find out the expression of width of the depletion region, let us first look at the charge neutrality of the depletion region. Now we have already discussed that the density of negative charges here is Na and density of positive charges here is Nd. Now what will be the charge density? Each negative ion will have a Q charge, so the total charge density here will be Qa and total charge density here will be Qd. Now we also know that this distance is xp and this distance is xn. Okay, now what is the total charge inside this region? So it is simple. Charge density is given as charge per unit volume. So what is the volume of this section? So let us say we have a PN material like this, a cylindrical PN material, and we have depletion region on the P side up to here. Let us say this is XP, and we have depletion region in the P side up to here. Let us say this is XN, so this is N side and this is P side, and this is your PN junction. Now let us say that the area, the cross-sectional area is A throughout. So what will be the volume of this section? So the volume of this section will be A times XP, right? And volume of this section, it will be A times XN. So the total charge in this section will be total charge density multiplied by volume, so A times XP. So this will be the total charge here, and the total charge here of this region will be charge density multiplied by volume. Now since there is only rearrangement of charges, so charge neutrality says that the total charge here should be equal to the total charge here. So you just equate these two. Okay, so by equating we can get that Q and AXP is equal to Q and D XN. Now we need to just rearrange and do some mathematics here, some simple mathematics to arrive at this expression. So if you look here, this is Q and AXP square. So this part can be made equal to q and a xp square if we multiply both sides by xp. So we have multiplied both sides by xp. Now this will become q and a xp square. This becomes q and d x and xp, and these two are equal. So in place of q and a xp square, we can put this, right? So we put this here, and then we rearrange a little bit, and then we arrive at this expression. Now similarly we do for the another term, for this term. So this is the charge neutrality condition says that this should be equal to this. Now to make it equal to q n d xn square, we multiply both sides by xn. So right hand side becomes q n d xn square, and this is equal to left hand side, and we can put this here, and then we can solve it to arrive at this expression. So you can do it in your notes. Now add these two. So this is xn square plus xp square plus xn xp plus xn xp. So we get xp square plus 2xn xp plus xn square, and on the right hand side we get this plus this, so we get this. Then this is simply qn plus xn plus xp whole square, and then we take square root of it to arrive at this expression. So xn plus xp is the width of the depletion region. Okay, here you can see xp plus xn, this whole makes w. Now since this expression is to find out the dependency of this depletion layer width on voltage here, so we can write it as xn function of v and xp function of v. Now xn plus xp is w, which is a function of v. So we just rearrange this, and you will get this very quickly. So you can do it in your notes, where w naught is this part. So this is your w naught. So what does this expression show? This expression shows that when you forward bias a PN junction, then by increasing the voltage, W reduces, or width of the depletion region reduces. So if this V is equal to 0, so W is how much? W will be equal to W naught. So at V is equal to 0, W is equal to W naught. Similarly, if you reverse bias this junction, what will happen? W will be greater than W naught. So this is the final expression for the depletion layer, and in the similar lines we have derived the maximum electric field. So this maximum electric field in the PN junction depends upon the biasing voltage. So if forward voltage is high, Emax will be lower. If voltage is reversed, that is PN junction is reversed biased, then it will become plus here, and then Emax will increase. Okay, that means what is Emax? Emax is this electric field which is maximum at the PN junction and reduces as we move towards the towards either side. So if you forward by this voltage, Emax reduces up to, let us say, here, and also the width of the junction reduces. So this width of the junction W reduces. Similarly, if you reverse bias the voltage, then reverse bias the PN junction, then Emax increases, and also width of the depletion region increases, right? So this can be seen from these expressions. Now what happens if you forward bias this PN junction? So this is also easy. Suppose that you have applied a negative voltage on the P side with respect to N side. So you reverse bias this PN junction. So what will happen? An electric field will set up in this direction. An external electric field will set up in this direction. Okay, and as we have seen, the width of the depletion region increases. Now what will happen to the minority charge carriers here? So the majority charge carriers here are holes, and the minority charge carriers here are electrons. So N P naught are the minority charge carriers here. So what will happen to these minority charge carriers? So on reverse biasing this PN junction, electrons will be pushed towards left in the P side region, and holes will be pushed towards right in the N side region. So this type of shape arises. Okay, so what happens here now, that as you can see, there is a gradient in density. So here density is very high, the density of minority charge carriers is very high, and here the density of minority charge carriers is lower, and here further lower, and so on. So because of this gradient, some leakage current will flow, because we have seen earlier that diffusion current flows when there is variation in the density of the charge carriers. So here charge carriers are very high, here charge carriers are lower. So because of these gradients, small leakage current will flow. So if some hole, for example, which are minority charge carriers here, somehow reaches this depletion region, although there are no holes here, but some of them may reach the depletion region, and when they reaches here, let us say a hole reaches here having a positive charge. So because of this electric field, these holes will be swept here on the P side. Similarly, if a small current flows and some electrons reaches the depletion region, so these are very small in number, but some reaches the depletion region. So as an electron reaches here, in the influence of this electric field, they will be swept towards the n-type region, and a reverse saturation current will flow. So reverse saturation current will flow, and you are already familiar with this current, as you already know about the characteristics of a PN junction diode, that the forward side it shows the exponential curve, and in the reverse bias condition a small leakage current flows, and then at some value of reverse bias voltage breakdown occurs. Now again we have rewritten the expressions for depletion, the width for depletion region. If we do not consider the polarity of the voltage, then for the reverse bias voltage this should be the expression, where if you increase this voltage here, the width increases. Okay, so similar is the case for Emax. So we have already seen this. but here we have just rewritten our equation considering that polarity of the voltage is not taken into consideration. So this is for reverse bias condition. So now we will derive the expression for the current density in a PN junction when it is forward biased, and it is given by this expression. So this is a forward biased junction as discussed earlier in this video. So now what will be NPX? NPX is the density of electrons which are minority carriers in the p side of the PN junction. So NPX can be written as NP naught minus NP naught. So this is NP0 actually. NP0 is electron density in the p side at zero distance from the depletion layer. So this is the electron density here. So this value minus this value, the electrons on p side at thermal equilibrium. So we get this value. So these are actually the charges or the electrons which flow from n side to p side. So they are this much, and then later when they diffuse into the p side, they get recombined with the electrons, with the holes, and their shape goes like this. Now you can see here that the shape is exponential. So this is the initial density, np naught minus np0 minus np naught, which is this value, multiplied by e to the power x plus xp by ln. So it is an exponential decay in the densities. Now the value of x here is minus xp. So this is minus xp here. So if you put minus xp in place of x, so what you will get? You will get 0, e to the power 0. So e to the power 0 is 1. So you are left with only this value in the box. So you are left with this value. So this equation seems correct. Now as x increases in the negative direction, it moves to minus infinity. Okay, so if you put minus infinity in place of x, so you will get e to the power minus infinity, which is nothing but 0. So this NPX goes to 0. So what does this mean? That NPX is not calculated from this axis, rather NPX is actually this axis carriers. So the axis for NPX is like this, and the y-axis is this only. Okay, so at minus xp, the value is this much, which is np0 minus np0, and at minus infinity the value of it goes to 0 because this is the axis. Now similarly it goes for the holes. As the holes moves from p side to n side, when the junction is forward biased, we get the maximum density here. So we get this expression. So this value is pn0 minus pn0, and this density decays exponentially as holes moves further into the n side and recombines with the electrons. Now this exponential, this curve is also exponential. So as we put x is equal to xn, which is here we have xn. So as we put x is equal to xn, we get e to the power 0, which is 1. So we are left with this value. So initially we have this much density, which is, now at x is equal to plus infinity. So if you put x equal to plus infinity, you will get e to the power minus infinity again, and it will become 0. So the axis for this is, x-axis for this is this much. Okay, so we are considering that our axis is here. So in that case, the expression for the axis carrier density is this much, and the expression for axis electron density will be this much. Now this NP0 depends on many factors. It depends on how much voltage you have applied. So naturally, if this voltage V is more number of holes will reach here, so this value will be higher. Similarly, and more number of electrons will reach the p-type region, and this value will be higher. So NP0 depends on applied voltage, and it also depends on the temperature. So this is exponentially dependent upon the voltage applied, and same is the case for holes. Now what will be the total charge stored inside this region or inside this region? So let us say this charge is Qn. So what will be the value of this Qn? So let us say we have this material here, and we have this PN junction here, and we have this depletion region in the P side. Similarly, we have depletion region in the N side. And this is our PN junction. So what is the total charge stored here? What is the total excess charge stored here? Because we are not talking about the charge in the thermal equilibrium. We are talking about the excess charge carriers, which are shown here. So the density is NPX, right? So this density multiplied by volume. So how do you find volume? Let us say that cross sectional area of this is A, so it will be A times NPX times dx, and then we integrate it over the whole x. So for left hand side, we'll integrate it from minus xp to minus infinity. So this will give you total charge stored due to the excess carrier minority electrons. So this is shown here. The only difference is that Qn is here charge per unit area, not total charge. Okay, so you can consider Qn as charge per unit area. Here it is total charge. So it is not simple mathematics. You can complete it in your notes, that NPX can be written like this. Okay, and in place of NP0 you can write this. So put this value of NP0 here, and then put this whole value here and then solve it. Now there is one mistake here. This is okay, this is Ln, where Ln is the diffusion length of the electrons in the p region, and this should be Lp, where Lp means diffusion length of holes when they entered and diffuse into the n region. So this should be Lp. So there is a mistake here, please correct it. Now this you have to do in your notes, and it is simple mathematics, and how we reach to this value on the right hand side. So just remember one thing, that in the last video we proved that Pn naught is equal to Ni square by Nd. Similarly, Np naught is equal to Ni square by Na. So you can use this to reach to this conclusion. Now this is an important concept, diffusion length of the electrons. So this is the average diffusion length, that when an electron moves from one region to the p sides, and then it recombines with the holes and then they diffuse. So the average length, you can say, is by which an electron travels in the p side. So this is diffusion length given by diffusion constant dn multiplied by excess carrier lifetime of electrons. So this we have already discussed earlier. Now this is the simple expression for diffusion current. This is the diffusion current by the electrons, and this is the diffusion current by the holes. So if we need to calculate only current, then we can write it like this: Qn total charge divided by tau n plus Qp total Qp charge divided by tau p. But here, as we have said earlier, Qn is charge per unit area. So if you divide both sides by area, then you get current density J. So this thing actually is written here as Qn. So probably I should have used different symbol than Qn, but this Qn is here, is charge per unit area. Now just put these values which you have obtained here and here, and then rearrange the values, because we have Np naught given by this expression, Pn naught given by this expression, and then you solve a little bit, or you can say arrange a little bit, and you will reach to this equation. So this is the exponential equation with respect to voltage, that the current density increases exponentially in the forward direction in the PN junction. So you are already familiar with this characteristics. You have studied it many times earlier in other courses. And this Js which you are seeing here is the reverse saturation current, which is actually the current which leakage current which flows, small leakage current, when the diode is in reverse bias condition, and at some higher value of reverse bias voltage breakdown occurs. So this whole expression is for the forward region, which is exponential, but this component here is showing the reverse saturation current or the leakage current of PN junction diode. Now that's all in this video. This is the reference from where I have taken my video content, and uh, this is also your textbook as far as the power electronic devices are concerned. Probably when power electronic converters will be discussed, we will be uh, quoting some other reference also, but for now this is the main textbook for the first two unit at least.